remotely. All right, so welcome to Math 150, Section 1, probably Lecture 6. So what we're going to do today is we're going to be doing limits. And so there's a lot of different ways you can choose to do limits. What I want to do now is talk a little bit about the general theory of limits, and then go into some examples as to how you compute them, and try to give you an overview of what's going on, what are the difficulties. You may notice that we are a little bit ahead in terms of the lectures of where we are for the homework. This is not accidental. I want you to have seen the material well before you have to do the homework problems so that you are not rushing. I know a lot of you sometimes have, lives, and you have events going on, and given that homework is due essentially every class, I want to make sure you have plenty of time to go and talk to either myself or the TAs if you have any questions before things are due. So that's why we're always a little bit ahead. All right, so definition of limits. How many of you have seen the Epsilon-Delta definition of a limit? Okay, when I was in grad school for a while, I was in charge of the undergraduate help sessions for math. And whenever they got to the Epsilon-Delta, it was basically all hands on deck. As many graduate students as we could get there, come on board. I will state what it is, but we're not going to really spend too much time on that. We're going to, for the most part, do limits mostly informally here. So we say a sequence xn converges to L if the limit as n goes to infinity of xn minus L equals 0. So the way you should view this is, as n gets larger and larger and larger and larger, I've got to be getting closer and closer and closer and closer. A more formal way of saying this is, I'm going to introduce some math symbols. This means for all epsilon greater than 0, backwards E, this means there exists a delta greater than 0 such that, I'm doing it this way. There exists an n greater than 0 such that if n is greater than n, then xn minus L is less than epsilon. The way you should view this is epsilon is your tolerance. I want to be within 1 billionth, 1 trillionth, 1 quadrillionth of the limit. And you tell me your tolerance, you give me the epsilon, it's a game. I then find an n and say, okay, if I choose my value sufficiently large, my index sufficiently large, then all of my terms will be within your tolerance. I got it within 1 over a billion. And they say, 1 over a billion is not quite good enough. I want to be within 1 over a quadrillion. Fine. I find a new n. And say, actually, I changed my mind. I want to be within 1 over a quadrillion squared. All right. And I find a new secret. So you give me any tolerance and I can get closer and closer and closer. This is doing it for a discrete sequence of points. You can also do it for a function. You could say, the limit as x goes to x naught of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0 such that if x minus x naught is less than delta, then f of x minus L is less than epsilon. And note, interestingly, when we do this, we assume x is not equal to x naught. So it's possible for the limit to exist, but not to be the value of the function at that point. That's not so useful for us sometimes, but we just look at all points other than, so x is going to x naught. It's not at x naught. It never reaches x naught. It just gets as close as you want to x naught. So x is getting closer and closer and closer to x naught, then the value of my function should be within whatever tolerance. So the way this is often drawn in terms of pictures, here's my function. Here's some point x naught. And here is what I believe the limit should be. You then give me some tolerance. So this would be L plus epsilon. This would be L minus epsilon. And what it's saying is there's going to be a small window about x naught, such that if I'm in that window, then the value of my function is within my tolerance of L. Now, if you note, I could be all the way down over here and still be within the tolerance. But then if I move a little bit, I'd be outside. I want to be within tolerance for the whole window. So I would choose some small delta coming down like this. And then we would say f is continuous at x naught if the limit as x goes to x naught of f of x equals f of x naught. Right? And that's what it will mean for a function to be continuous. Right? So basically, you're the limit if you're being approached. Okay? There's an Eagles song we could have played right now, but I don't think Eagles would count as 80s, so I will not do the Eagles. All right? What kind of properties, what kind of questions might you want to ask about a limit L? What might you want to know about the limit? So you want to generate good questions. What's a good question to ask about the limit?
Why do we use this definition?
So we'll use this in proving a lot of results in calculus. But what's a question you might want to ask about the limit?
Whether it exists.
Whether it exists. So sometimes the limit will not exist. So the first question you might want to ask is, does it exist? All right. That's the first question, existence. Let's assume the limit exists. What's your next question? Yes?
Is it continuous?
Well, the limit, you might be talking about a specific sequence. So what does it mean for the limit to be? So you might ask, is the function continuous? You could ask that. But what might you ask about the actual value of the limit?
Is it a finite number or infinity?
Okay, so if it's infinity, we typically say it doesn't exist. Sometimes you talk about diverging to infinity. But you might want to ask, is the limit unique? Could a sequence converge to two different limits? We have a really strange light switch here, where the lights can be in different states with the switch in the same state. I've never seen a light switch like this before. If I have a sequence, do you think the limit is unique? Or do you think a sequence or a function could converge to two different values? Yes?
Not a two-dimensional, not a function with one independent variable and one dependent variable, but a multivariable function maybe.
Well, what does it mean to converge to a limit? It means as you go further and further down, as time passes, you get closer and closer and closer. Can you be getting closer and closer and closer to two different points?
Yes. Yeah, like an asymptotic function.
But I want to be getting closer and closer and closer to these 2 points simultaneously. So imagine, are limits unique? So let's do an example in two-dimensional space. Let's say here's L1 and here's L2. And I want my sequence to be converging as n gets very, very large to both L1 and L2. Or if I'm talking about, that's I guess a vector value function, I could be talking about maybe a function on the real line. So I have my sequence. Here's L1, here's L2. I've got to be getting very, very close to L1, and I've got to be getting very, very close to L2. If they're not the same, there's some separation between them. Let's say the separation is half a unit. Choose 1/1000th for your epsilon, so that those neighborhoods are disjoint. Well, if I'm converging to L1, eventually all terms in the sequence have to be within 1/1000th of L1. If I'm converging to L2, eventually all terms in the sequence have to be within 1/1000th of L2. And since they're separated by more than 4/10000000, I can't be simultaneously close to both of them. So it's a nice exercise. Write this up rigorously, but limits are unique. You cannot be getting arbitrarily close to two different points. As time passes, if you're getting very, very close to L1, eventually you are separated from L2. Okay, any questions about this? So this is a really nice property, that if the limit exists, it's unique. The hardest question is to figure out what is the limit. So amazingly, there are many times when we can prove a limit exists without being able to prove what that limit actually is. we can just show the limit must exist. This is not the greatest. Imagine you are a politician and you want to win. And your campaign manager tells you, good news, I found there's a winning strategy. What is it? I don't know the details. I just know that there's a way for you to win. Well, that's not necessarily helpful. Sometimes, however, in mathematics, it's enough to know that something exists, and once you have the existence, you can argue in generalities. How many of you have seen the mean value theorem? So the mean value theorem is a wonderful example of something where we know that such a special point exists, but we don't necessarily know where it is. Well, when we prove the fundamental theorem of calculus, we'll use the mean value theorem to get us a point with a needed property. And it turns out we don't actually need to know what it is. It's just nice to know that it exists. Let me give you one of the most important examples of a sequence that has a limit, and we can compute the limit. And so what we're doing now is we're putting in a little bit of material for later in the semester when we really do sequences in series. The geometric series. So consider 1 plus r plus r squared plus r to the n. And I'll call that, xn. So these are going to be called partial sums. I'm just summing 1 plus r squared all the way up to r to the n. And I want to know, as n gets very, very large, does this sequence converge? And so there's a beautiful formula. If xn is 1 plus r to the n, r times xn is 1 times r is r times r is r squared, r to the n minus 1 times r is r to the n, and then r to the n times r is r to the n plus 1. There is a way to prove this formula by playing a game of basketball, which we might do later in the semester. So if I subtract, notice how all the terms in the middle cancel, and you get 1 minus r to the n plus 1, and then you get 1 minus r times xn, just doing some algebra. So you get xn is 1 minus r to the n plus 1 over 1 minus r, or I can write it as 1 over 1 minus r plus r to the n plus 1 over 1 minus r. So this is a formula for xn, an explicit formula. And now if I let n go to infinity, what happens to this term? So what would happen to that term? So as n goes to infinity, what does r to the n plus 1 go to? Or do you need more information? It depends. So if r is less than 1 in absolute value, what does it do? It goes to 0. If r is greater than 1 in absolute value, it goes to infinity. So if the absolute value of r is less than 1, then xn is going to converge to 1 over 1 minus r. And we can even see what the error is. One of the most common mistakes people make is they use formulas in situations where they have no right to use them. What's 1 plus 2 plus 4 plus 8 plus 16 going all the way up to infinity? What does that equal? I'm adding all the powers of 2. What should that equal?
Infinity.
Everybody get infinity? No. What's the actual answer?
Infinity.
Nope. -1. It's so large it goes past positive infinity, starts at negative infinity, and almost makes it back to 0. What the hell is going on? How did I get -1? Yes?
Did you do this slope thing where you...
No.
I used the formula, right?
I used the formula with r equals 2. So 1 over 1 minus 2 is -1. Amazingly, in advanced mathematics, formulas like this make sense. And there is a way to interpret this as -1 as meaningful. Should we be a little bit skeptical of the sum of the positive integers being -1? Yes. And the great financial meltdown of 2008, 2009 was people were using math formulas without checking the conditions were verified before using them. And you got into this terrible situation where the more bad loans and mortgages you combined together, the better credit rating it got, which encouraged people to bundle more bad things together. It was terrible. So always be aware of when you can use something, and always ask, is this answer reasonable? You know, when you see the sum of positive numbers being -1, you should be a little skeptical. Okay? So we are very fortunate with the geometric series in that we can look at it, we can write an explicit formula, we can see what the limit is. Sometimes you can prove a limit exists without knowing what it is. Frequently you have some idea of what the quantity is. And then there's a lot of rules to calculate limits. So you've seen a lot of these before. And so, you know, there didn't seem to be any questions, so I'm not going to go into too many of them. But limit of a sum is what? So the limit of a sum should be the So all of our calculus laws derive from limit laws. So if I give you the sum of two functions, what's the derivative of f plus g?
F prime plus g.
F prime plus g prime. The derivative of a sum is the sum of the derivatives. What should the limit of a sum be?
The sum of the limits.
The sum of the limits is the sum of the limits if at least one is finite. And this is where you have to be a little bit careful. What's the limit as x goes to infinity of x minus x? So what would this limit be?
0.
0. What's the limit as x goes to infinity of 2x minus x? Infinity. And what's the limit as x goes to infinity of x minus 2x? Negative infinity. But if we split this up, the limit, okay, I'm saying some difference is the same thing. The limit of a sum, if that's the sum of the limits, well, I have the limit of x, which is infinity, minus the limit of x, which is infinity. So in this case, I would get infinity minus infinity. In this case, I would get infinity minus infinity. And in this case, I would get infinity minus infinity. We can't deal with infinity minus infinity. There's a couple of things that are just flat out we're not allowed to deal with. We cannot deal with infinity minus infinity. Can we deal with infinity plus infinity? Yes. You have infinitely many dollars in the bank, and a friend gives you infinitely many more. Wonderful. Right? Life is still good. You have infinitely many dollars in the bank, and you give infinitely much money to a friend. How much do you have left? Well, now it's no longer so clear. What's infinity times infinity? Infinity. What's infinity times 0? That's another one that's unclear. So we have to be very careful. So these are the places where, you know, we're going to get to the results in calculus. So what you want to say is the limit of a product is the product of the limits if at least one exists. And by existing, I'm basically meaning finite. Because again, consider the limit as x goes to infinity of x squared times 1 over x. Or the limit as x goes to infinity of x times 1 over x squared. Yes?
So does that mean that 0 and infinity and negative infinity, the answers that we got in the first place, are invalid because you can't do
Well, for this one and this one?
Well, the 0 and like
This one?
Like we talked about the fact that you can't subtract infinity from infinity.
Right, we cannot subtract infinity from infinity, but I can look at x minus x. So here, I'm just saying x minus x is 0, and now I'm taking the limit.
Okay.
What I can't do is I can't say that this is equal to the limit as x goes to infinity of x minus the limit as x goes to infinity of x. I can't split it up like that. And I can't split this one up, and I can't split this one up.
I see. Oh, because then, okay, I understand.
But as long as I keep them together like this and do the algebra, then I'm fine.
Okay, that makes sense.
So we just have to be very, very careful. Similarly, the limit of a product, you want to say it's the product of the limits. That's true so long as at least one is finite. The limit of a quotient is the quotient of the limits. Any other caveat we need?
So long as one is finite.
So we need a little bit more than so long as one is finite. What else do we need for the, yes?
And the divisor is not 0.
And the divisor, the one in the bottom, is not 0. Right? We are not allowed to divide by 0. Okay? So we have to just be careful about limits like that. All right. Let's do a couple of limit problems. Let's look at the limit as x goes to infinity of 3x squared plus 4x minus 9 over 8x to the fourth minus 2x minus 2. So what do you think this looks like as x goes to infinity? Yes?
Goes to 0.
It goes to 0. Why?
Because the exponent in the denominator is greater than the exponent.
Yeah, so basically the denominator is killing the numerator. So the question is, how do you see this rigorously? Well, as x is going to infinity, one good idea is pull out an x squared from all the terms up top, pull out an x to the fourth from all the terms down below. This is the same as the limit as x goes to infinity. I'll have an x squared, then I'll have a 3 plus 4 over x minus 9 over x squared, divided by x to the fourth, 8 minus 2 over, pulling out an x to the fourth, so there should be x cubed, minus 2 over x to the fourth. And now you can see, as x gets very, very large, what is this piece looking like? Just this part in the parentheses. 3. And this part down below. 8. So this part is looking like 3/8, and then x squared divided by x to the fourth, that looks like a 1 over x squared. And so as x goes to infinity, you'll have 1 over x squared essentially times 3/8. That will be 0. Okay? So for problems like this, you want to just pull out the highest power you can of x. All right. So the next question is, what happens now as we go into multivariable calculus? So we could ask, well, what if we have a function of several variables? What does it mean for the limit to exist? And so how many of you have seen Karate Kid 2 again? I thought some people had seen Karate Kid 2. No one has seen?
A long time ago.
All right. So in Karate Kid 2, I don't want to give it away too much. I will just say you learn the secret of Miyagi karate. When you are in one dimension, limits are boring in one dimension. Why are limits boring in one dimension? What are the possible paths you can take to approach a point? Left or right. It's boring. There's really not that much to check. You have 2 paths to check. When I first started teaching multi, I had students who would always get personalized scribbles from my kids and their preschool friends. And I would just have all the preschool kids make scribbles. So they would go, converging onto a point. This is the secret of multivariable calculus limits. All right? This is the Miyagi karate moment. When I say the limit exists, it must exist along all paths, including this one. Now, in one variable calculus, there's not that much to check. Go this way. Go that way. Done. There are infinitely many paths to check. We need a good formal way to go through all these paths. We do not want to have to explicitly write down what the hell path that is taking. Okay? But that's essentially what we need to do. When a limit exists now in multi-dimensions, it means a lot more. And what we'll see later on when we start doing differentiation, which we're getting very close to doing, is it's not enough to just check, do the partial derivatives exist along the x-axis? Do the partial derivatives exist along the y-axis? That's not enough to imply the function is differentiable. If the partials are continuous, it's enough. But if they're not continuous, it could be the case that the function is not differentiable. It's only differentiable in those special directions. you need to be able to look at every possible path. And that's extremely annoying, having to check every possible path. So we want good ways to do this. Okay. So there are a couple of things we need to do. The first is, well, what if we have a vector valued quantity? And so essentially, if you have a vector with 3 components, what do you think must be true for the limit to exist? Yes?
The limit must exist for each component.
So it must exist for each component. So it's exactly what you would expect. If I have something that has 3 components, each component must converge. If I have 5 components, all 5 components must converge. And then all the results you have follow similarly. If I have 2 vector sequences and I add them, the limit of the sum will be the sum of the limits so long as they exist. And everything just proceeds as before. The interesting thing is when you have a function now of several variables, what does it mean for the limit to exist? So let's look at the limit, say xy goes to 0, 0 of x squared plus y squared over x to the 4th plus y to the 4th. So do you think this limit exists or doesn't exist? Yes.
Doesn't exist?
Doesn't exist. So if it doesn't exist, you have to give me 2 paths that have different answers, or you have to show that it goes off to infinity. So which do you think it is? So can you give me a path where it goes off to infinity?
I think, was it the other one with 2 limits?
I'm sorry?
The one that, you said earlier, not like when it goes off to infinity, but like when you can get 2 points that you can say that are different.
Right, so you have to give me 2 different values. If I have xy approaching 0, 0 in 2 different ways, I get 2 different answers. So can you give me 2 different ways? Or can you just show that there's a path where I get infinity? So what do you think the easiest paths are to check? Yes?
Along the x-axis?
Along the x-axis, along the y-axis. Check those first. And then if those don't work, you can check y equals ax. But just because it passes those tests does not mean it will work in general. You start to become more and more confident. But I can actually give you a nasty limit that works along all straight lines and all quadratics, but fails along cubics. So you can have some strange stuff going on. So if I take y equals 0, I get x squared over y to the 4th. Oh, what does that do? That just blows up. So if take the path of y equals 0, you get the limit as now x goes to 0 of x squared over x to the 4th, which is infinity. So that's enough to show. I'm sorry?
Is that infinity?
Yeah, you're gonna get 1 over x squared.
Right.
So this is enough to show the limit doesn't exist. Okay? Let's try another one. Let's try the limit as xy goes to 0, 0 of x squared minus y squared over x squared plus y squared. So do you think the limit exists or it doesn't exist? What are your thoughts? What would be a good path to take? So these should be your go-to paths. What's our first path to take?
Like 1, 0.
I'm sorry?
Like 1, 0.
Okay, so you have to let the x go. You have to have something going to 0, 0. So you could take, for instance, just y to be 0, and just take the x-axis. So if I take y equals 0, what do I get?
1.
If I take x equals 0, what do I get?
-1.
-1. And if I take x equals y, what do I get? If x equals y,
0.
0. So if I take the path of y equals 0, that leads to a limit of 1. If I take x equals 0, that leads to -1. And if I take x equals y, that leads to 0. I have 3 different answers. So depending on how I approach 0, 0, I get 3 different values. So limit, people often write DNE for does not exist. Okay? So again, if you want to prove something doesn't happen, if you want to prove the limit doesn't exist, it's sufficient to find two paths where you get different answers. Limits are unique. If you have two paths giving you two different answers, then you have to be does not exist. But what if you find two paths that give you the same answer? That doesn't prove the limit exists. It's just you're beginning to get more and more confident. The more paths you take and the more times you get the same value, the more confident you are. But it's not a proof. Remember, Miyagi Karate, or I guess I gotta go like this now so we can see. Remember Miyagi Karate. You have to take all paths, including that monstrosity. Do you want to calculate that monstrosity? The way we often do something like that is we would switch to polar coordinates. And what you would do is you would replace x as r cosine theta, you would take y as r sine theta, and then you would say, if I want xy somehow converging to 0, 0, what would that mean for r and theta? So if xy goes to 0, 0, what would that mean for r theta? Yes?
Wouldn't it just mean that r converges to 0?
So this means r goes to 0, and what about theta? Can theta do whatever the hell it wants?
Yeah.
Yes, theta is free. Theta can have fun. Theta can give us whatever this nightmare is, but just shrinking down. So this is a really good way to often explore what's happening as xy goes to 0, 0. Convert to polar coordinates, allow theta to do whatever it wants, and then just show that as r goes to 0, the resulting quantity goes to 0, or goes to whatever the value of the limit is. So let's do another one. Let's do the limit as xy goes to 0, 0. Let's do x to the fourth plus y to the fourth over x squared plus y squared. What's our first path that we should try?
X equals 0.
All right, so if we try x equals 0, we get y to the fourth over y squared. That's just y squared. That goes to 0. All right. What if we try y equals 0? Then we get x to the fourth over x squared. What if we try y equals ax? If we try y equals ax, we would get the limit as x goes to 0 of x to the fourth plus a to the fourth x to the fourth over x squared plus a squared x squared. What will that go to? Well, it's the same as the limit as x goes to 0 of 1 plus a to the fourth of x squared over 1 plus a squared. Because I can just cancel out an x squared. So what will that go to? It'll go to 0. So we've now shown that the limit is 0 along any straight line. Have we proven the limit is 0? No. We have to consider again the Miyagi paths. Okay? Let's now switch to polar coordinates, and let's see what things look like if we move to polar coordinates. So now let's take x is our cosine theta, y is our sine theta, and now our limit is going to be the limit as r goes to 0, theta is free, of r to the fourth cosine to the fourth theta plus r to the fourth sine to the fourth theta over r squared cosine squared theta plus r squared sine squared theta. Oh, great. Well, what's the denominator? What's r squared cosine squared plus r squared sine squared?
R squared.
It's just r squared. We have an r to the fourth, so we can divide by an r squared. This is the same as the limit r goes to 0, theta is free, and we'll have r squared, and we'll have cosine to the fourth theta plus sine to the fourth theta. Does this limit exist? cosine to the fourth theta plus sine to the fourth theta. As theta does whatever the hell it wants.
Yeah.
So for every path, for every choice of how theta varies, will this part have a limit? No. Imagine I take theta to be pi halves. Imagine I take theta to be pi. Imagine I take theta to be pi fourths. I will get different values. So if I come along your straight angle, I can get different values for this. So unfortunately, if I want to say the limit of the product is the product of the limits, I can't quite do that because this limit doesn't exist. Is it bad that this limit doesn't exist? What can you tell me about this quantity? What kind of values can this take on? What's the smallest cosine to the fourth plus sine to the fourth could be?
0.
0. And what's the largest it could be? It's okay to overestimate. What's the largest it could be? You don't have to give me the best answer. What's a weak, easy answer for how large it could be?
2.
2. Right? Cosine and sine are at most 1 in absolute value. Could this be as large as 2? No. Could you go through and use your calc skills to figure out how large this is by taking derivatives and finding critical points? Yes. Does it matter? No. As it doesn't matter, I don't want to do it. There's advantages to being the professor. It's somewhere between 0 and 2. So I take this number r squared, and I multiply it by a number that lives somewhere between 0 and 2. Well, if r is going to 0, r squared is going to 0, and 2r squared is going to 0. If you want to write this really formally, it's called the sandwich theorem. So we would have the limit as r goes to 0 of 0r squared is thus equal to the limit as r goes to 0 of r squared cosine to the fourth theta plus sine to the fourth theta, and that's thus equal to the limit as r goes to 0 of 2r squared. It lives between these extremes. If this extreme goes to 0, and this extreme goes to 0, and this lives in between, there's only one thing left for it to do. It has to go to 0 as well. Right? Because this quantity here is always at least 0r squared, and it's never more than twice r squared. So as r goes to 0, whatever this quantity is, it has to be sandwiched between these two extremes. This extreme goes to 0, that extreme goes to 0, so this must go to 0. So no, we're not saying the limit of the product is the product of the limits. We can't do that because the limit of the product doesn't, one of the terms doesn't exist. But we don't need it to exist. And if we needed it to exist, this would be a very, very painful course. And we would have to compute all these things. The idea is only compute what you need. You know, this is dominated by 2r squared. Well, 2r squared goes to 0. I don't really care exactly what this is. Let it fluctuate. Not a big deal. Okay? So any questions on problems like this? So again, when I'm getting ready for the lectures, if there are specific examples you want to see done, you can say, could you do this example from the book, or could you do this example from the exercises? And as long as it's not a homework problem, I'm happy to do it. Or if you want to see a homework problem from your last class, happy to do that. So is there any material, any specific problems people want to see? Okay, so we're now in the situation where we can calculate a lot of limits. Okay? And so there's going to be, not surprisingly, some homework exercises asking you to calculate limits. The polar trick is a really good trick to calculate limits. And then, as I said, a function is continuous if it equals its limit. A function doesn't necessarily have to be continuous. Anybody know a good example of a function that's not continuous? Yes.
Step function.
Step function. You always want to have go-to examples. So a step function is a great example of a discontinuous function. So it's equal to one value, and then all of a sudden at some point it changes instantaneously to another. And the question is, how might you define it in between? So for a step function, maybe before 0, it's equal to 0. Beyond 0, it's equal to 1. And then the question is, do you have freedom in terms of how you define it at 0? And there's no good way to define it. If you had to choose, what would you choose? If you have to assign some value to the function, it's 0 here, it's 1 here, what would you like to assign it at 0? Yes?
It depends which direction you're coming from.
Yes, and you don't know which direction you're coming from. So what do you want to, so how would you decide a value? You have one value. You got to give it a number. There are 3 natural candidates. One is the best of the 3. What would be a good value for the middle?
1/2.
1/2. Right here. Make it 1/2. Split the difference. I don't know which way I'm coming from, but the function will not be continuous. Do you know a really good example of a non-differentiable function? So yes.
Oh wait, actually, isn't there something with the absolute value?
Yes. Yes, the absolute value is the standard example of a non-differentiable function. And it's only non-differentiable at one point. And we will see later in the semester how bad it is that this function is not differentiable. So let's look at f of x equals absolute value of x. So it's x. If x is greater than or equal to 0, it's negative x. If x is less than or equal to 0. I know I've defined it twice at x equals 0, but the 2 definitions match, so it's okay. And if you plot the function, here's the plot. And so now if I try to calculate the derivative, I want to look at the limit as h goes to 0 of f of, say, 0 plus h minus f of 0 over h. If I take the derivative, if I take h to be positive, I'm going to get a slope of 1. If I take h to be negative, I'm going to get a slope of negative 1. So it equals plus 1. If h goes to 0 with a plus sign, that means from above. It equals minus 1 if h goes to 0 with a minus sign from below. So this function is not differentiable at the point 0. Depending on how I approach, I get 2 different answers. All right, we've got a few minutes left. Let me review a technique from calculus that's often very useful for calculating derivatives. Let's take the limit as x goes to infinity of x over e to the x. Anybody remember how we would take this limit?
Lhopitals Rule.
Lhopitals Rule. So if you have 0 over 0, infinity over infinity, you can L'Hopital it. If you are a really good scientist, your name becomes a verb. Right? You L'Hopital this, and this is the same as the limit as x goes to infinity. What's the derivative of x?
1.
What's the derivative of e to the x?
E to the x.
And so you'll just get 0. So the exponential function grows faster than the polynomial x. If I did x squared, who do you think would win? X squared or e to the x?
E to the x.
E to the x. It would just take how many L'Hopitals?
2.
2. If I gave you x to the 2018, how many L'Hopitals would we take?
2008.
2018. So really, any power. All right. What about this one? The limit as x goes to 0 of the sine of x over x. How would you calculate that limit?
Same rule.
Okay. So what are you doing? You are using
L'Hopitals
You're
Rule.
using L'Hopital. X goes to 0. What's the derivative of sine of x?
Cosine.
Cosine. And what's the derivative of x? That's 1. Cosine of 0 is
1.
1. Does everyone agree with this? Seem good? Yes?
You're allowed to use Lhopitals Rule with any indeterminate form, right? And 0 over 0 is...
0 over 0 and infinity over infinity. That's, you can't use L'Hopital if you have 2 over 2 or 5 over 5. You can only use L'Hopital if you have 0 over 0. And once you no longer have 0 over 0, infinity over infinity, you have to stop. Okay. How many of you have seen L'Hopital's rule before? Okay. There is a slight technical point here. How do you know the derivative of sine is cosine? You got this from differential trigonometry, right? What's the limit you need to calculate? You need to calculate the limit as h goes to 0 of the sine of 0 plus h minus the sine of 0 over h. What's the sine of 0?
0.
So this is the limit as h goes to 0 of the sine of h over g. That looks a lot like that with the x's replaced with h's. So the way we know that the derivative of sine is cosine is by calculating this limit. So you have to be really careful about when you've learned things. It turns out that this derivative, that this limit equals 1, is the most important derivative in all of trigonometry. Everything else follows from this. But you've got to be very, very careful. And it's easy to forget what was assumed and what was not. So this is L'Hopital's rule. Okay? And so I will just state L'Hopital's rule formally. So L'Hopital's rule. If the limit as x approaches some point x naught of f of x over g of x is 0 over 0 or infinity over infinity, then the limit as x goes to x naught of f of x over g of x is the same as the limit as x goes to x naught of f prime of x over g prime of x. Assuming, of course, f and g are differentiable. If f and g are not differentiable, you can't use L'Hopital's rule. And then if you still have 0 over 0 or infinity over infinity, you apply L'Hopital again, and you keep doing it until you no longer have 0 over 0. So this is terrific for solving a lot of one-dimensional limits. If you have a two-dimensional limit, well, we don't have a two-dimensional L'Hopital. Okay? All right, any other questions or examples? All right, so we've got about 1 minute left, so I'm just going to throw something in the bank that some of you may have seen. How many of you have seen the Moivus theorem, stuff like that? E to the I theta? So this is extremely useful for the differential trigonometry to make everything rigorous. And so I'll just state it now. E to the I theta is cosine theta plus I sine theta, where I is equal to the square root of -1. We will do a lot more with this later in the semester when we get to Taylor series. It's worth seeing it now. It leads to what some people consider the most beautiful formula in all mathematics. E to the I pi is equal to -1 because it involves three of the most important concepts, E, I, and pi, all together. So we will give a sense of why this is true, and I will actually teach you how to use this to derive every trigonometry identity. So how many of you love memorizing trig identities, like the cosine of the double angles and the half angles and all that? I will show you in about 1 minute how to get every trig identity essentially from this equation. All right, so that's just a little bit of a precursor. All right, have a good one.